Hey everybody, welcome to the first Math 350 video, complex analysis. Now before we get into complex analysis, which deals with things like and our complex numbers and everything, I want to do a quick recap on multivariable calculus because a lot of complex analysis actually relies heavily on what we learned back in 250 or multivariable calculus. Now quick note, this is not an exhaustive list though, so I'm just going to get through some of the things that we will need in the immediate future for Math 350. But again, this is not an exhaustive list because there's no way you can review Math 350 in a short video. In any case, let's go ahead and get started. Okay, so multivariable calculus deals with not R, but usually Rn, so higher dimensional Cartesian space, if you will. But what we're going to focus on today is more of R2. So remember R2, which for those of you that have taken Math 322, this is the Cartesian product of R with R, okay, is just two-dimensional space. Okay, so you can think about R2 in two ways. So geometrically, it's points in a two-dimensional plane. So for instance, 1, 1, -1, -1. Or maybe something with a little bit more kick to it. Let's say, I don't know, something like over here, this would be probably -e, 0. I don't know. Something with a little bit more flavor to it, though. Another way you can think about R2, if you think about this Cartesian product, it's just the set of all points, x, y, such that x and y are both real numbers. Okay. So I would say this is more of the algebraic viewpoint. And then over here, this is the more geometric viewpoint. Okay. And you want to be comfortable with both because we are going to be using both in some capacity in Math 350. All right, another way of thinking about points in R2, you can actually give them a vector structure. So let's say let's go back and look at our point 1, 1. So I can think about the vector that starts at the origin and ends at the point 1, 1. Okay, so every point in R2 can be thought of as a vector in this way, where you start at the origin and then you go to that point. Now, the reason why we like vectors have sort of more properties than points do. Vectors have two additional things. They have a direction. Okay, and what I mean by that is basically where is the vector pointing at? And two, vectors have length. Or sometimes you'll hear magnitude. Vectors have length. So a vector, yeah, it is an arrow, but there's important properties about that arrow. There's a length to it. Okay, so our length in this case would just be this distance here. Okay, which would be, for those of you that know your trig, that should be square root of 2 in this case. And they also have a direction, so where are they pointing? Now there's a lot of things we can do with vectors, so let's go ahead and consider u equal to u1, u2, v equal to v1, v2. So the first thing we can do is we can add vectors. Now I'm going to go through this all algebraically. You can also think about this geometrically too with parallelograms and things like that, but in any case, I'm going to do this algebraically. So as an example, a running example, let's go ahead and let u be 1 minus 2, v equal to, I don't know, 3 minus 3. Yeah, there you go. All right. So what we can do with vectors is we can add them. Now what's nice about adding vectors is just component-wise. So if we're going to add u and v, it would just be, well, 1 plus 3, comma, minus 2 minus 3, also known as 4 minus 5. Another thing we can do with the vector is we can scale it, meaning we change its length by some scalar, for lack of a better word. So for instance, if we consider, I don't know, just the number 2, okay, we can take 2 times u, which is just going to double the length of u. Okay, algebraically, what is it going to do? You just multiply all your coordinates by 2. So 2 comma negative 4. Okay, so this would be scalar multiplication. So again, yeah, so we can add vectors, and we can also scale them as well. So stretch them or shrink them. We can also define the length of a vector. So there's two common ways I've seen this pop up in 250. I believe I think I used both there as well, but sometimes we call the length of a vector with double brackets, or I should say the notation is double brackets like this. Or sometimes we just use, and this is usually because it's easier to write, we just use single brackets. And actually this is going to be more common in Math 350 here. More common for us. Oops. Now how do you find the length of a vector? So this is given by the Pythagorean theorem. You just take the square root of the sum of the squares of the components. What a mouthful. Okay, so in our case, let me put a little bubble here. The length of u would be equal to the square root of 1 squared plus negative 2 squared, which is the square root of 5. I had to think about that for a second. Now notice length is always a positive quantity, so if you're ever getting anything negative, double check your work for sure. The last thing we can do with vectors, which we may not use as much, by the way, I'm trying to get dust off of the tablet. Another thing we can do with vectors is what's called the dot product, u dot v. And all this is, first of all, it's going to give you a number, okay? And to calculate this number, all you do is you multiply like coordinates, almost like a FOIL, and then you add that together. So in this case, if we're dealing with two-dimensional vectors, this will be u1, v1 plus u2, v2. By the way, does anyone like the band U2? Anyway. So for our example over here, u dot v, this would be equal to 1 times 3 plus negative 2 times negative 3, which will give you 3 plus 6, which is 9. Okay. Now, if you remember back in 250 or multivariable calculus, the dot product is a really, really awesome tool that'll tell you some geometric properties about your vectors. If this number is positive, that means the angle between the two vectors is acute. If it's negative, the angle between the two vectors is obtuse. And then if it's 0, we know that the vectors are perpendicular. Okay, so we actually get a lot of geometrical information about two vectors given this dot product here. Okay, kind of rushing through math and multivariable calculus here. So now we're on to limits. Okay, so remember, limits in multivariable calculus are I would say a lot more, I don't know what the best word is. They're a little bit more complicated than I would say single variable limits. And the reason is we kind of have a lot more to account for. So for instance, example, let's say we were taking the limit of, and I got to think of a function here. Let's just say x plus y over x minus y. Okay, and let's say we're taking the limit as xy goes to 0, 0. Now the reason why limits are a little bit more complicated, and by a little bit I actually mean a lot more complicated than Calc 1 limits, is because if we're taking the limit to a point, in this case we're taking the limit as xy goes to 0, 0, we have infinitely many ways we can approach this point. And I know I'm just taking lines right here, but we can be even more creative. Maybe we go along a parabola. Maybe we circle the point twice and then attack it this way. But there's literally infinitely many ways we can approach that point, whereas in a Calc 1 limit, we take the limit as, let's say, x approaches 0 of, I don't know, x over x squared. Okay. There's only two ways you can approach 0 in R, right? You can either come from the left, so you have the left-sided limit, or you can come from the right. However, in Calc 3, when you're dealing with these multivariable limits here, we have a lot more to work with. So that makes limits a little bit more complicated. So proving limits exist, usually you either want to use some kind of algebra, or you want to use continuity, which we'll talk about in a second, or you can use what we call the squeeze theorem, or sometimes they call it the sandwich theorem, depending on where you're going to. If you want to prove limits don't exist, and this is what I really want to touch upon today, you want to consider paths. Okay, so to show a limit, I'm going to be brief here. DNE does not exist. show limits down paths give different results. D-I-F-F-E-R-E-N-T. There we go. Results. Okay, so I picked this problem x plus y over x minus y in particular because I know that this is not going to exist. Okay, so let's go back to this limit here. Let me try to pull up really quick. I'm going to get rid of that circle there. Okay, so if we want to show this doesn't exist, well, we can do, actually, let me erase some stuff. Goodbye, all my beautiful paths here. Get out of here, get out of here. Okay. Did not mean to do that. All right, so to show that this limit does not exist, remember we're taking the limit as xy approaches the origin there. So we can think of a couple of paths that approach the origin. We can approach the origin from the x-axis, okay, i.e., if we're along the x-axis, that means y is 0. We can approach 0, 0 from the y-axis, which means x is equal to 0. If we want to be really pinkies up, we could travel along a parabola, for instance, i.e., y equals x squared. Or, in this case, we could actually, if we want to get trig involved, we can go along the path y equals sine of x, although we're not going to do that here, because why do that? But in any case, we could do it theoretically. Okay, so for this limit, what we're going to do, we're going to keep it kind of nice. We're just going to consider the two paths along the y-axis and the x-axis. So path 1, okay, we're going to look at the limit as xy approaches 0, 0 along x equals 0, so the y-axis in this case. And then what is our limit going to go to? Well, if we think about our function here, we're going along x equals 0, right? So that'll give us 0 plus y over 0 minus y, which if we simplify this here, we're just going to get negative 1. Okay. Now what happens if we go along the x-axis, though? Okay, so if we take the limit as xy approaches 0, 0 along, okay, now if we're going along the x-axis, y is 0. What are we going to get? Well, if we think about our function again, if I plug in, or if we're going along the x-axis, we're really just left with x plus 0 over x minus 0, and then that'll give us positive 1. The x's will cancel out in this case. So what did we just show? We showed that if you traveled along two different paths, you got two different outputs, okay, or you got two different limiting values. Okay, so that means that our limit does not exist. Okay. So remember, review these ideas if you need a little bit of a refresher, but this is what we're going to be doing, and we're going to use this idea in 350 at some point, but it's important to make sure that if you're unclear of limits, go back to your multivariable calculus notes. We will see it again. Continuity in the multivariable case is very similar to single variable case, so we say that a function is continuous at a point if the following three conditions hold. So first, and this is always what I tell students to check, your point needs to be in the domain of your function. Is in the domain. If your point is not in the domain, automatically your function's not continuous there. 2, the limit as xy approaches x naught y naught of your function. Okay, so if we take the limit to the point we're looking for continuity at, if this exists, okay, or this needs to exist, I should say, for this function to be continuous at that point. And then lastly, not only do we want the limit to exist, we want the limit to be equal to the function value. Okay. So there's three conditions that need to hold again for continuity. 1, your point needs to be in the domain. 2, your limit needs to exist at that point. And then 3, the limit exists and it's also equal to the function value. Okay. Sometimes in calculus books you'll see all three of these conditions in one condition, which is basically number 3 here, because implicitly condition 3 here actually is saying that, one, your point is in the domain. That's from this left or right-hand side. If the limit is equal to the right-hand side, then automatically the limit exists. But I like to break it out, though, for students because these are 3 check marks that need to hold, and it's good to think about them. Because you can really quickly, if one of these don't hold, you know automatically it's not continuous there, especially number 1 here. Now, for a lot of the functions we deal with in Calc 3, continuity sort of comes down to a couple of things. One, if you're just dealing with a regular function, not a piecewise function or anything like that, usually a function is continuous as long as it's in its domain. So for example, if your function, if f of x, y is a polynomial, a rational function, or has some kind of trig, exponential, logarithm, amalgamation, or it's kind of some, I don't know, has either trigs or exponentials or something into them. So I'll just put that at sort of like has trig, exponential, or logarithm. So if our functions have these forms here, then f of x, y is continuous on its domain. On its domain. So if you're dealing with, for instance, a polynomial, maybe you're dealing with f of x, y equals x squared plus y squared plus 2xy. I don't know, something like that. Then we know that we can polynomials are continuous on their entire domain, so this function would be continuous everywhere in this case. Rational functions, for instance, if we're dealing with kind of like that limit we just looked at, f of x, y equals x plus y over x minus y, we would know that this function is not continuous where we blow up the universe when x minus y equals 0. Now note, when x minus y equals 0, what does that mean? That means x equals y. So this function here would be continuous everywhere except for when x equals y, because that's when we Thanos snap or blow up the universe there. Okay? So a brief refresher on continuity, but again, continuity requires 3 different conditions to hold. And if we're dealing with our sort of our classical functions, like polynomials, rational functions, things that have trig, exponential, or logs in them, your function is usually continuous on its domain. Now, if you're dealing with piecewise functions, then you got to be a little bit more careful, and you got to really use your limit definitions. All right, partial derivatives. So hopefully everyone remembers this and loves this, but partial derivatives, they're taking derivatives with respect to one of your variables, and you're treating the other one as a constant. So for instance, let's look at the example, f of x, y equals 2x squared y plus x plus cosine of y. Let's say we wanted to take the partial derivative of this with respect to x. So df, and notice I'm going to try to use curly d's here. Df dx in this case would be, so we're going to take the derivative of the right-hand side with respect to x, and we're going to treat y like it's a number, like it's a constant. Okay, so the partial of f with respect to x would be 4xy plus 0, because y is a constant, plus 1, and then plus 0 again, because if y is a constant, cosine of y is for sure a constant. So in this case, we would just get 4xy plus 1. The partial of f with respect to y, same idea, except now we're sort of shifting our attention to y. So we're going to take the derivative of this expression with respect to y now, and we're going to treat x like it was a constant. Please let me write. There we go. Okay. So again, we're going to take the derivative of the right-hand side with respect to y, so we'll get 2x squared, okay, because again, x is a constant, so 2 times x squared is also a constant, plus 1 plus 0, plus derivative of cosine is minus sine. So our partial with respect to y would be 2x squared plus 1 minus sine of y. Okay. So partial derivatives, kind of broad strokes, you're taking the derivative with respect to one of the variables, and at the same time you're treating the other variable as a constant. Now, if you remember back in multivariable calculus, the reason why we care about partial derivatives give you a sense of what the function's doing in the direction of one of those variables. So for instance, the partial of f with respect to x is telling you how is the function moving when you're going in the direction of the x-axis. Df dy here, this is what your function is doing in the direction of the y-axis. Okay. with respect to the y-axis, I should say. So it's giving you directions in a way. Well, it's giving you what the function's doing in directions. All right, last thing I wanted to bring up, polar coordinates, and this is we're gonna see this pretty early in 350. So remember, polar coordinates are a different way of thinking about points in R2. And this is just R2. Polar coordinates don't work for R3. Well, we do have cylindrical coordinates, which is our R3 polar coordinates, but polar coordinates, just think R2 in R2. So we usually think about points in R2, so let's call this x comma y. Okay. This would be called Cartesian coordinates, but we think about these points as, well, you go x units along the x-axis, and then you go y units along the y-axis, and you arrive at this point, right? So you can kind of think about this point as sitting at the sort of the vertex of a rectangle. So that's how we normally, so this is normally how we think normally. Sometimes you call this rectangular coordinates as well, rectangular or Cartesian coordinates. Okay, so that's how we normally think about points in R2. We think about them as x comma y, where x is how far you go along the x-axis, y is how far you go along the y-axis. So again, you can kind of think about your points as sitting at the vertex of a rectangle. Now in Calc 3, when you're computing integrals in particular, sometimes it's not easy to integrate, or sometimes it's impossible to integrate a function in this coordinate system. Okay, and that's where polar coordinates really get their or why we care about polar coordinates, at least in Calc 3. Polar coordinates allow you to visualize points in a slightly different way, and that can make integration a lot easier. So instead of thinking about points as lying on a rectangle, we think about points as lying on a circle. Okay, so let's say this is our same point. Okay, so instead of expressing it in terms of how far are you along the x-axis and y-axis, we think about it as, well, what would the radius of this circle be? We'll call that r. And then what would be the angle here between the x-axis and, well, our terminal point here, our terminal vector here. We'll call this theta. So we think about this point as lying on the circle of radius r. That makes an angle with the positive x-axis theta. Okay. Now you can actually choose different thetas. Like we could have picked theta to be, well, we go around one more revolution or what have you. We're not going to get too much into that, but in any case, that's a way you can think about this point, though. So it's sitting on the circle of radius r, and it makes an angle with the positive x-axis theta. Okay. So this is what we would call polar coordinates. Polar coordinates. Okay. So remember, we do have some conversions, and this is all coming from SOHCAHTOA and trig. So we have that r squared is equal to x squared plus y squared. That's coming from the Pythagorean theorem. We have that tangent of this angle, and this is the TOA part of SOHCAHTOA, is y over x. I'm going to put here TOA. Tangent is opposite over adjacent. That's where that formula is coming from. X is equal to r cosine of theta, and then y is equal to r sine of theta. So these would be our conversion formulas for going back and forth. Conversion formulas. Okay. Now the reason why I bring up polar coordinates, we are going to see, well, there is a way we can think about complex numbers in terms of polar coordinates. But I want to get you used to the idea that we can think about points in different ways. So we have in R2, we have two ways that we commonly think about points. We think about them either in rectangular coordinates or in what we call polar coordinates. And the reason why you would pick one over the other, it just depends on what you're doing. In some cases, it's easier to compute an integral in polar coordinates, or sometimes it's possible to do it. Sometimes we like to integrate it in normal coordinates. It's kind of the same idea in 350. There's situations where we're going to want to think of a complex number in this way, and there's going to be situations where we want to think about it in another way. And you want to get used to that concept. We're going to be able to, or we're going to want to use different representations for the same point. All right, that's a really quick review of Math 350. or multivariable calculus. We'll pick up a little bit. Well, we'll talk about other things as we move along in the course, but that should hold us over for a little bit at least. In any case, if there's anything in this video that you were a little iffy on, make sure you review your Calc 3 notes. And in any case, we'll go ahead and get started with complex analysis in the next video.